Okay, I think we can get started. It's the final talk today. Madsen will tell us something about epistemological mediation on the bias-variance tradeoff.
Yes, or we'll not just talk about it, but even perform it or live it. Before I start with my slides, I'll just try to explain what the topic of this talk is. It comes out of this perennial debate in statistics or epistemology generally, which is how we represent the uncertainty we have about hidden factors or hidden variables in the world. You're typically in a situation in statistics or elsewhere where you have some observation, you want to learn something about a hidden cause or something like that. And there are two different camps in statistics, the frequentist and the Bayesian ones, where the frequentist says that you should treat this very cautiously as a logical variable, and then you should try to learn things about learn some relatively weak statements about this based on your observation. Where Bayesians say this is just a random variable, just like the output variable, the observed variable is. So you internalize it into the model, and everything is just a probability distribution. So everything is treated by the same language and in the same way, and this makes for very powerful reasoning systems. But it's a slightly more heavy-handed assumption as well. And in particular, it requires you to choose a prime probability distribution for the variable. And this you sort of have to pull out of a hat with no justification from anywhere. And this has always been a source of concern for frequentists, and in some cases for Bayesians as well. And they've often been criticized for being very unscientific or arbitrary or even worse names than that on occasion, because they just seem to assume things that have no statistical basis and could actually influence the answer that the model would come up with. So what I'm going to talk about is the bias-variance dilemma, which is a sort of a glimmer of hope that maybe there's actually something to be said for having models that have kind of an opinion on their own. So models that before they see any data, they already have suspicions about what's going to happen, and they're only gradually convinced that the world is otherwise as they get lots of data. And this, even though this sounds like a design flaw in a model, this can actually be a quite good thing. So it seems like there might be something like a justification for having arbitrariness in the design features you have in your statistical models. But what I'm going to show you is that this is not quite going to work out. Not because it's sort of mathematically wrong, but because it's inconsistent with some basic tenets of Bayesian philosophy to invoke this argument. It essentially requires you to say it's okay to treat this as a probability distribution, as a random variable, if we think about it as a logical variable. So there's a kind of conceptual incoherence built into such a justification. And the way I'm going to go about doing this is roughly historical, but a little bit of historical fiction built in. So I'll try to give you the conventional picture of sort of in the beginning of the 20th century, why everybody was thinking bias was a bad thing in statistics. And then the quite shocking discovery that actually having biased models could be a good thing. And then talk a little bit about this philosophical issue that comes up. But let's start with a little problem. Does anybody have an answer? Just shout a number.
34.
34. Any other numbers?
More than 17.
17? Right. I was lucky. These were just the two ones I put on the slides. Okay. So those are two possible rules you could use for trying to guess, if you have to, what the actual number of tanks is, or 1 minus the number of tanks minus 1. Okay, so we had the double, the 34, and we had 17. One of them actually has higher probability given, or the data we saw had higher probability given one of these guesses, namely the lower one. So if you have 15 tanks and you say, then observing the number 14 has 1 over 15 as probability. If you have 34 tanks and you observe the number 14, then it's 1 over 34, or 35 tanks, I guess that would be. So this one has an advantage in the sense that it assigns higher probability to the data. And if you had a probability distribution, if you were a Bayesian over n that assigned higher probability to lower army sizes, then it would also have a higher a posteriori probability. Okay, but this was not the first one, and I had to sort of step on your toes to get another number. And why is that? Why does it seem like a bad idea to shout 14? Well, here's one traditional explanation. Imagine that we repeated this experiment over and over and over again. I secretly, on the back of a piece of paper, wrote down a number n. Then I randomly chose a number between 0 and n, and I gave you that, and you had to guess. Okay, so one half of you says 2k. That would be this one. Right, so you have estimates that look like that. You only use even numbers, so 0, 2, 4. And the other half, you always shouts k back. So I say 17, you say 17. And it looks like this. So this is for a fixed n. So I had an n here, perhaps 12 or something. So no, I had an n here of 8 in this case. So in one case, when this is the actual truth, I pick a number n. One team k over here, will have a probability distribution over their estimates, the numbers they shout, which looks like this. So they always shout a number which is smaller than the true value. And the 2k team will have a probability distribution that looks like this. It only contains even numbers, which is kind of strange, but it's symmetrically distributed around the actual true value. So if you compute the expected value of the estimate, in one case it's n halves, right, for a fixed n, the actual size of the top of the army, and in the other case it's n. So one of them, on average, you'll coincide with the actual true value, and with the other one, on average, your estimate will be half the size of the actual value. So this seems like maybe a desirable feature to build into a system. And that's the motivation for defining the bias, or if we will, the squared bias of an estimator. In this case, we use n with the little hat as an estimate of n. So this will be the actual value of n minus the expected or the average estimate. Okay. So I repeat the same experiment lots of times with lots of German armies, and every time I report what you shout back to me, and I get an expected value for that number. And that, in an unbiased estimator should then be one that coincides perfectly with the truth on average. Although, as you can see, it can be spread up like this. So that seems like that would be a nice thing to have for an estimator. Another example, which is sort of more classical classroom statistics, is if you have a Gaussian distribution, and it has a mean, and it has a variance, and we don't know any of them. And we then select, say, 3 different samples from this distribution, and then let's suppose we estimate the mean of the Gaussian just by taking the average. Then we can estimate the variance in 2 different ways. So one would be to take the empirical average of the squared deviation from the estimated mean. That would seem reasonable given that the definition of the variance is that it's the expected is the expected square deviation from the actual mean. So that's sort of an obvious and naive way of going about it, which is doing this. And then there's a wacky way of doing it, which is subtract n, 1 from n, the denominator. And it turns out in this case that actually if you use the one where you don't subtract 1, you get a consistently lower estimate for the variance. Which if you think about it just for a little while, is not so strange because you always compute the average deviation around the estimated mean. So you pick the mean that has the lowest deviation. So in a sense you estimate mu in a way that brings this number down as far as possible. So you're sort of pushing it down a little bit too much. And if you subtract 1, then you're bringing it back up to a more correct level. So in this case, with only 3 variables, they vary quite a lot. This is for 100 data points, but this one is significantly better than the one where you don't make the correction. Okay, so this is a biased estimator. On average, it misses the mark. And this is an unbiased one. On average, it coincides with the truth. So that's good, and you can imagine having a whole branch of statistics that just thinks about these issues. And indeed, we not only had that in frequency statistics, where we sort of, again, in classroom statistics, where we learn about it, but also Harold Jeffries on the Bayesian side spent a lot of energy thinking not exactly about biases and things like that, but about designing priors that had minimal assumptions. So models that indeed did have an opinion on their own, but a very modest and quiet opinion that didn't impose itself on the data. So there was a quite heavy consensus at this point that bias is really bad. And if there's any way you can build that out of your model selection, you should do that. Okay, so let's think a little bit about a different issue here. Which one is the unbiased one? I have a coin that maybe it has like counts up heads 0.7, like 70% of the time. Then I have 2 different methods for estimating that, or for guessing that 0.7. One is to just, if it says heads, I say 1, and if it says tails, I say 0. That's one method. The other method is always just say 1/2, whatever the data set is. So just throw out the data. Which one is biased and which one is unbiased? Well, this one is certainly biased. It has a very, very strong opinion on its own. And in the case of 0.7 at least, I mean, it could be unbiased if you were lucky enough that the actual truth was 1/2. But in all other cases, it's going to be biased. This one, it turns out, is actually unbiased. Because and if you repeat the whole experiment, picking new coin a gazillion times, then 0.7 times 1 gazillion times, it'll come up heads, and you'll answer 1. And 0.3 times 1 gazillion, you'll answer 0. So the average of that is going to be the actual parameter, very close. So this one is completely unbiased, has bias 0, and this one is biased. But if we look a little bit at how well we do on an individual level in the experiment, so we look at the actual parameter value, then the guess that we look at, and then we take the square error. So this deviation between the two is a random variable. And if you have the one where you always respond 0 or 1, then there's a random variable that has 2 values with probability 0.7 and 0.3. So this is the mean squared error. So it penalizes very large errors, and it's always positive, and it's 0 if and only if you always guess correctly, deterministically guess correctly. So if you plot this for different values of theta, you get a graph like this for the empirical average. This is the one where you always report 1 or 0. And the red one is the one where you deterministically just guess 1/2 whatever the data set is. So what's a little disconcerting about this graph is that it's actually a larger area of the unit interval in which the deterministic guess is better. So something like 0.15 up to 0.85, you're actually better off guessing just 1/2 whatever the data set is. And only in these very extreme cases are you better off going by the data you actually saw. So that seems a little weird. Here's something even weirder. Imagine you have a normal distribution again. It has a variance of 1. This is fixed and publicly known. And then an unknown mean, mu. So somewhere on the real axis we have a mean. You get one data point. Okay, in this case, 3. What's the what would be your estimate of mu? Is there a natural choice? 3 would be a pretty natural choice, it seems. So let's try that out. So that would be x. Just return the single data point you have. That seems like a quite good idea. And indeed, as before, that's an unbiased estimator. But we could also just slap a constant in front of it. Say, why don't we just squeeze it down a little bit towards 0? I really like 0, so let's go a little bit in that direction. Or use a different scaling constant if we like. So for no particular reason, I select the number 0 and say, that's my favorite number. Let's take the data point wherever it is and pull it a little bit towards 0. So if you compare, or I could go back here. So here's the actual mean. Then the data point you see could either be to the right or to the left of the mean, but you're always dragging it towards 0. So if you think a little bit about when the unscaled version is better and when the scaled version is better, you're always doing better if the actual mean is positive and you're on the negative, data point is on the negative axis, right? Because then you're being pulled up. So that's always good. If you're, and there's a threshold here which is slightly larger than the actual mean. And if you're to the right of that, then being pulled downwards is good. If you're here, it's obviously bad because you're going away from you. If you're here, then it also turns out to be bad because you're sort of being pulled in a wrong way. Okay, so once you have that, you can compute what the probability is for a specific fixed mean mu, that you'll get a better estimate by the unbiased estimator compared to the biased one. And it turns out that it's actually only a tiny little interval around 0 where unbiased estimation is better. For the whole unbounded rest of the real line, you're better off using the biased estimator. Right? So, and a priori didn't make any assumptions about mu. So if you use the unbiased estimator, you're actually making a bet on this event here happening. And you can make this as small as you like just by making this constant closer to 1. Okay, what's even worse is this. So this is the so-called James Stein paradox or James Stein phenomenon. So now we're in 3-dimensional space. We still have a fixed variance. And then someplace up there, some 3-dimensional point is the mean point in space. And then you've got some random Gaussian noise around that with variance 1 in all directions. So again, the obvious thing to do is just to use your data point as the mean estimate. But you can also use this kind of strange scaled version, which uses, not as before a random constant, but uses the length of the vector as a kind of modifier that squeezes things down. It turns out this estimator is better everywhere. So at the exact point 0, 0,0,0, they're equally good, the two estimators. And everywhere else in 3-dimensional space, this biased estimator is strictly better than the naive estimator. Okay, so in some cases, we can say with certainty you're positively being hurt by being unbiased. You can actually only improve your performance by introducing bias if this is your inference problem. So this was a bit of a shock back in the 1950s when people noticed this. So why is this the case? Well, let's be theoretical about this. So there's a theorem which is called the Bias-Variance Tradeoff, which is a theorem in frequency statistics that says that the mean squared error you have can be decomposed in this way. So there's the squared bias, which we already had here, and then the variance of the estimator. So the variance of the estimator measures when you have your gazillion different German armies, how different are your estimates going to be in all of those cases. So if you had a robot that could only say 1/2, 1/2, 1/2, 1/2, then it would have variance 0, but a very high bias percentage. If you had one that was extremely data sensitive, then it would have a very high variance because it would just run after the data set constantly and chasing the noise as if it were real information. So you have a picture sort of like this. The blue cross is the secret parameter value that you're not being told. And then each of the red dots here are supposed to be the estimate you make after seeing a data set. So there are multiple dots, not because it's a big data set, but because I've repeatedly drawn big data sets and had you shout an estimator back to me. Okay, so one way of thinking about this is that the parameter itself is just a fixed constant, but then because we add noise, it sort of fluffs up to a cloud, or your estimates fluff up. So the data sets fluff up to a cloud around that. And you want to bring it down. Ideally, you would like to end up in this situation, right? Just be almost deterministically at the right value. But the only way you can squeeze down that cloud to something like a constant is by saying something like, I really like the number 0. Let's all be closer to that number. If you do that too much when you're wrong, the number 0 is actually not the correct value, then you're not doing very well. If you do it when you're just right, then that's perfect. Right? Then you make yourself more deterministic while you were correct. But if you were wrong in the first place, then it's actually better to have a slightly higher variance so that you at least occasionally hit the right value. So there's a kind of conflict between how much bias you can, or how much variance you have and how much bias you have. They're both bad in a sense, or at least unless you know what the value is, in which case you wouldn't be doing statistics in the first place. Both of them are kind of bad. You don't want to be biased away from the correct value, and you don't want to have too much of a variance, because that means you're taking the noise too literally. The reason why this is the case is a kind of Pythagorean formula. So we're measuring something like a distance between the estimator and the true value. So you can walk directly, take this step, or you can take an intermediate step. So the way we do this is to first take the direct step, and then say, let's insert a waypoint here in the middle. So we subtract and add the average estimator. And then you multiply that out, and you get one term here with a square, another term here with a square, and then a double product. Right? Like a plus b squared is a squared plus b squared minus 2ab. Maybe I have a... Oh yeah, I flipped one of these. This is why the sign is different. Right, so if you look a little bit closer at that formula, you'll recognize that one of the terms is the variance of the estimator. One of them is the squared bias, as I wrote it up here. And then one of them is a sort of oddly looking term that's a little bit like a covariance between two things. But it's not quite a covariance because they're not around then this one should be replaced by the mean of the actual parameter value, which does not make sense when the mean is a constant. But it does measure, in some sense, a kind of linear relationship between two things. However, it's the case that this expected value is just a number, it's a constant. And since we're doing frequent statistics, this theta is also just a fixed constant. We're conditioning on some unknown with a fixed constant value. So everything in this parenthesis is just a constant, so you could move it out here. And then you have the expected value of theta minus the expected value of theta. So this whole thing cancels if you think that theta is a constant. You don't think theta is a constant if you're a Bayesian. Then it's a random variable, and you should take that into account when you take expected values. But if you think that it's a constant, then this term measuring the information transmission between the actual value and the estimator, that just disappears and does not make a difference. So that's all from a theoretical perspective why this is the case. So one example here, the German tank case, is where you have the two different estimators. One is just k, one is 2k. And then it turns out that I think in this case the 2k one does better for all but the numbers 0 and perhaps 1, something like that. But you can compute the bias, and we found out that 2k was an unbiased estimator. It has a bias of 0, and then the variance. And obviously this one is going to have a higher variance because it's spread out more. But still, because it has such a low bias, it turns out that it's going to be better on average. With the coin flip, the case looks like this. That you have 0 bias again for the one that just returns the observed value. You have 0 variance for the constant one, obviously, because it's a constant. So this one is just the variance, and this one is just the bias. So that's again the mean squared error, the sum of the two that I just plotted here was the same graph that I used before. So for each value of theta, each fixed value of theta, you could take the sum of those two, and that would be the mean squared error in that possible world. All right, so this could lead you to think, well, so maybe arbitrariness is not such a big problem if you're a Bayesian or some other kind of statistician dealing with the real world. You're making a bet anyway, right? So there's no problem in having picking a prior that's centered around 0, has a specific variance rather than another variance, because it's all embedded in a huge big pile of uncertainty. And in some cases, having a high bias can actually be a good thing, because there's way too much noise compared to the information you get from the data set. Or in some cases, you want to be very unbiased, because the world is actually complex, and you should listen to the data instead of insisting on everything just being equal to 1/2. So this was his argument in this case for why it's a good thing to have like very simple heuristics or very high biases in the way of kind of from a mock evolutionary standpoint. But in other cases, you can find similar in the machine learning literature, similar claims made more directly about for rationale for arbitrariness in prior probability distributions. So that seems nice, except that all of this depends on us being frequentist. Right? I'm conditioning on theta being a single fixed constant. And Mr. Ronald Fisher, Sir Ronald Fisher, has no problem with that. That's like the foundation of his whole edifice. But Sir Harold Jeffreys is decidedly not happy about this. There's only one rational calculus of uncertainty, and that's probability theory. If you're using anything else for quantifying or expressing your uncertainty, you're committing a sin against rationality. So he would not condone this this kind of reasoning. And in fact, he would probably say something like, well, that's a very nice mean squared error you produced for me. Let me just average it over my prior probability distribution that I've chosen for the parameter. So he'll get rid of theta by integrating it out instead of conditioning it on it. So then the whole thing is not a gamble on anything. You're not supposing something or assuming something about the world. You're just using some features of your prior probability distribution to compute a single number that tells you how well or badly you're doing. And that number is not a random variable, it's a constant that measures your performance. So let's look at an example here in a little bit more detail. So I've got a biased estimator here, which consists partly of, again, an empirical average, a single coin flip, and I divide it by 1. And it consists partly of the constant 1/2. And so I put some weight on the sensitive one and some weight on the stubborn one. And I want to know what the optimal value of B is, assuming that we're using a flat prior probability distribution of the parameter of the coin. So that's just computing, as we say in statistics, right? And no thinking, you just turn the crank. So you expand that expression, and you integrate out the parameter you're not interested in, and then you get this expression, and you find out when that one is, where it has a minimum, which is for B equals 1/3. So if you're doing a single coin flip, then you should pick your bias to be, with weight 1/3, you should be biased towards, let's say 2/3, you should be biased towards the constant 1/2. And that's just, the debate ends there in the Bayesian framework. There's no making decisions under uncertainty or being fearful of what might happen or whether assumptions are ill-founded or something like that. Or a different example here. So first I pick the parameter according to a triangular prior, and then I pick the data point according to another triangle. So then you get this. So again, there's a bias and there's a variance. And then there's the informational term that tells you how much they talk together, the estimator and the actual parameter. So now notice this is not 0, right? Because we're not talking random variables anymore. We're not talking constants anymore. These are random variables. So there's a statistical relationship between the estimator and the parameter because both of them are random. So you can just read off what the numbers are, right? Say, oh, I better choose x divided by 1/2 as my estimator. So scrap the unbiased one and scrap the completely data-sensitive one and pick the one that's just in the middle. So it's a maximization problem, or a minimization problem, if you will. So that might lead you to think that everything is all well, but the problem with this argument is that what it really consists of is you saying, well, again, we have our data set, which is conditioned on a parameter. But then perhaps that parameter has some extra parameter up here, which we're not treating as a random parameter, but as a logical constant, like the choice of prior probability distribution. So we can use a frequentist argument to justify our choice of prior probability distribution, and then have no uncertainty down here, or you have two options, right? Either you don't do any of that, you don't use the bias-variance dilemma as would be like the, I guess, option number 0, and then you can't even talk about your uncertainty in qualitative terms in a Bayesian framework, because if you have any uncertainty, you've already expressed it in terms of a probability distribution. You don't have any other language. So you either look like this, in which case the optimal estimator just falls out completely. You just compute which one is the best. Or it looks like this, and you've secretly smuggled in some concern about whether from a non-Bayesian, non-probabilistic standpoint, your probabilistic assumptions were correct. So you're either, let's say, sinning against your philosophy or against your math. That's a little bit simplified, but you can get both interesting points about generalization out of the bias-variance dilemma and a completely committed Bayesian of this magnitude. So, with the last slide here, that there's certainly something about this, right? It's an interesting piece of theory from frequency statistics, which shows us that there's something going on with being biased, where you want to combat noise in some sense by loading the die. And then you might think that this would get you out of trouble for having completely arbitrary priors when you're a Bayesian. But this is really a kind of incoherent argument in that you either have to take prior on faith, or you have to build more priors, hyperpriors, or quantify other extrinsic sources of uncertainty in terms of probability distributions as well. Well, you've got to be lax about something. Either you're be less philosophically strict than this guy, or actually build a mixed model and start arguing in some other way, in which case you're really, maybe that's too much to say today, there's a frequentist, but there's certainly a frequentist wrapper around your Bayesian theory. All right, but that's what I have to do.
Commentary by, as you can see, Richard Pettigrew, who couldn't make it due to some Eurostar issues, but who was nice enough to send his commentary, so Juman will present the commentary.
I'll have to warn you that he actually emailed me the comments as well, so I already read them. Or warned you, I guess.
So I can't add anything.
You can perform.
I'm going
You are now an actor.
Okay, so comments on Madsen's epistemological meditation on the bias-variance tradeoff. Firstly, apologies to Matthias and everyone for not being able to give these comments in person. This is a really interesting paper. The core mathematical observation is that while the frequentist must think of mean squared error as the sum of variance and squared bias, the Bayesian must not. From this, Matthias draws the philosophical conclusion that while there is a bias-variance trade-off for frequentists, that is, the frequentist must choose between minimizing bias and minimizing variance, there is no such trade-off for the Bayesian. The frequentists who wish to minimize both bias and variance must pick an estimator and take a leap of faith, quote unquote, that is the right one. That is, that its mean is also the target parameter. For the Bayesian, there is no room for leaps of faith. I have a couple of observations to make, one mathematical, one more philosophical. The mathematical observation. Let's return to Matthias's proof that mean squared error equals squared bias plus variance. You have that on there?
Yep.
Save me from writing that. Okay, so
This one.
yes. So first we expand the usual definition of squared error. So, squared error is no. Okay.
just without the outer mean.
Yeah,
I
if you
guess.
take off all is everything inside. Yeah, so that, then we note that the mean squared is this, and of course this ultimately boils down to bias squared hat plus variance. Now, Bias says that the following crucial identity, which allows us to remove the final term, is valid only if we treat theta as a fixed value. So that's the theta hat. Two. Expectation.
It's sort of like writing Lisp code.
Yes. Okay, so yes, so this crucial identity allows us to remove the final term only if we treat theta as a fixed value. Since the Bayesian does not treat it as a fixed value, but rather as a random variable, the Bayesian cannot make this move. Under one interpretation of Bayesianism, that's correct. If we take the Bayesian to calculate all of the expectations in the above proof, using a joint distribution on x, the data, and theta, the parameter, then the identity just stated does indeed not always work. We might call this the subjective expected square error. Since all of the probabilities that are used to calculate the expectations are subjective probabilities. However, it is not clear that this is the natural Bayesian approach. It is perhaps the extreme subjectivist Bayesian approach of the sort championed by Finetti. But it is not obviously the moderate Bayesian approach of the sort championed by Lewis, where objective probabilities are used when known and subjective probabilities fill in the gaps. Here's an alternative, which I take to be closer to moderate Bayesian. The Bayesian calculates the mean squared error exactly as the frequentist does, assuming that theta is a fixed value. After all, it is a fixed value, though it is unknown. This gives gives us that, as above, where each of the expectations is calculated with respect to the objective probability of the data conditional on the parameter theta. This gives us a value for the mean square error that has theta as a parameter. The Bayesian then applies a subjective product distribution over the possible values of theta to give the subjective expected mean squared error, which is the just take the expectation of both of those separately, which then reduces just to the expectation of this plus variance. Thus, the moderate Bayesian does seem to have a bias-variance trade-off after all. For her, the bias term of an estimator is the subjective expected squared bias, where the squared bias is calculated using the objective probabilities. Driving that quantity down entails driving up the variance and vice versa. So that's the end of the mathematical observation. The philosophical observation is much briefer. In his concluding paragraphs, Matthias writes as follows: But if we do represent our uncertainty as a probability distribution, it is important to keep in mind that all questions, including questions about estimation methods, have definite answers that follow mechanically from the features of the models. In a consistently Bayesian philosophy, there is, strictly speaking, no room for leaps of faith. So, Pettigrew continues, yet it seems that it is precisely the assignment of a prior probability distribution that is the leap of faith to Bayesian. They assign one, they pick the unique estimator that is recommended, then they hope that it is successful. At least for the extreme subjectivist, they could have picked some other prior distribution, just as the frequentist could have picked some other estimator. And had they picked some other prior, it may well have led them to a different estimator that might have worked better. I don't know, does that have a good impression?
All right, so let's take the philosophical comment first, because that one's the easiest to address. So this is true. You can be, as I said, you can be a frequentist about how to choose priors, and you can experiment a little, or you can think a little bit about the robustness of different priors, and look at try to find logical principles for using priors. But all of that, I would say, is quite un-Bayesian, or at least very different from what De Finetti is arguing for. I think he would be very explicitly adverse to anything like that. And we do actually, there's a funny quote that I found by David Blackwell recently, who said that that all the work on empirical Bayes back in the 1970s, I guess, was a big step forward, but perhaps not in the right direction. And I think this is sort of a very parallel issue, that this idea that you have to infer something about a probability distribution in order to use it is a fundamentally un-Bayesian idea, and can't be integrated into the theory without tweaking something so that it doesn't look like itself. I think that's what I have to say about the philosophical issue, unless somebody has questions. Then there's the issue about maybe you can be a frequentist in the first part of the computation and then take expectations with respect to theta afterwards. And I can't think of any way that would make sense in the context of a larger model. I mean, I did email a little bit with him, and he suggested this, and he said he would explain it to me when he was here.
He'll be here tomorrow, so
yeah. And well, David Lewis it doesn't help very much. I mean, everything he says about probability is so nonsensical. I mean, if you are thinking, as I think you should be, if you want to treat both of these as random variables, about a joint distribution over the data sets and the parameters, then you can't just forget about, or condition for 5 seconds and then integrate out for another 5 seconds. That's mathematically incoherent on any interpretation I can think of, at least. You might. It's sort of related to suppose you have your frequency is about something. You don't know where there's an unknown number theta that tells you, but has some influence on how much money you're going to make in your job, and it could have any real value. So the whole axis is in play, and you have, so you don't know which one it is. So you just integrate over the whole axis and hope that that number comes out being meaningful or signifying something, but it doesn't really signify anything. I mean, Ronald Fisher wasted a lot of energy back in the 1950s and 40s trying to. I mean, he kept saying that this would make sense, and it became increasingly clear to all of the students, and I think to everybody but him, that it really made very little sense. He kept changing the interpretation of this to cover that up. One of the commentators, the Bayesian commentators at the time, said you can think of something else to say, but you can't think of anything else, just think. And
You can't whistle it either.
what?
You can't whistle it either.
Yeah. Okay. Yeah. So maybe if we had something more specific to go by, or I could say something less dismissive. No, because but I don't know exactly whether there's some like maybe he has a rabbit in her head. I don't know.
Good, Katie.
Yeah. Okay. Thanks. I enjoyed reading this paper. It's nice and brief, but I had to read it several times, and I had increasing moments of enlightenment, which is, I think, always a good sign. So I guess in this commentary I'm going to focus more on interpretation, right? So the sort of distinction between classical methods and Bayesian methods is a big interest of mine. So that's kind of what I was focusing on when reading the paper. And also, the reason I had to read it so many times is because I'm not used to dealing with estimators, right? So as a philosopher, you kind of spend a lot of time jiggling with probabilities over hypotheses in the Bayesian framework, but it's a bit more foreign to think of this notion of estimators and their average performance or expected performance. Okay, so I'm just going to start from the beginning and just rehash a little bit of what Matthias was doing. The first figure was very helpful to me. This is the first thing Matthias just drew up as well when he was talking. So we have some property of the world, right? So some parameter that governs the distribution of a random parameter, right? The probability distribution. But this is supposed to be a property of the world, like the chance of heads of a coin in the world. Right? Now, this gives rise to distribution. It specifies the distribution of various evidence that we might get in the coin case. We'll get sort of depending on what experiment we're doing, we'll get a sequence of coin tosses, right? So we've got some data, and we use this data to estimate this value, right? So this is actually a function of the data. And this might be for the coin case, we might estimate the chance of heads as just heads over the total tosses. That would be one estimator, or we might do some modification of that, heads plus 1 or 2, I forget what.
Well, one upstairs and two downstairs.
One upstairs, okay.
You've got two buckets, and you give one
Yeah.
bonus point to each of them.
Okay, so it might be some modification of just heads over the number of tosses, right? Now, the classical statistician, I mean, this is the way I think of it, they're sort of obsessed with kind of objective things in the world, right? None of this looking into people's minds. We want our inferences to have sort of objectively good properties, right? So for the classical statistician, the world is some way, right? And these various estimators have an objective performance in terms of their average error in the long run, right? And you can think of their performance as also facts about the world, right? So given that the world is a particular way, various estimators have different long-run average squared error, right? And this is also a fact about the world. So ideally, we want to use the estimator that has the minimum squared average error that's a fact about the world, right? We want to pick the objectively best estimator. Now, of course, the problem is we don't know the way the world is, and depending on how the world is, different estimators are objectively the best, right? So that's the kind of pinch for the classical statistician. And Matthias showed some examples where, depending on where you were in terms of the true value, different estimators were coming out as objectively best. And really, the classical statistician doesn't have that much more to say at that point. Just say, well, you know, unfortunately, that's where the objective information gives out, and so you just have to sort of take a stab, I guess. Maybe they'd say it a bit differently. Now, the Bayesian can actually come up with a uniquely best estimator, but it's no longer the objectively best estimator. It's what you, as the experimenter, given your, this is the way I think, but I think maybe Matthias thinks a bit different, given your prior beliefs, which we also add, about the actual true value, it's what you expect to be the best estimator. Right? So it's no longer an objectively best estimator in the world, just what you expect to be the best estimator given your probability distribution, your initial probability distribution of the way the world could be, right? And the performance of these estimators given those various ways the world could be. Right, so we've introduced this extra subjective element for the Bayesian. I'll come back to that, right? So much of the interest of the paper, I think, is showing that this nice expression, which is really the frequentist expression. I mean, very interesting, really, that the mean squared error for the frequentist is this sum of the square bias, sort of how far the expected value of the estimator differs from the true value and the variance of this estimator, right? This is all very interesting, and then Matthias shows that actually for the Bayesian, it's not an equal sign, but rather less than or equals, because you have this extra term on the end, right? Okay, so now just for some brief comments. The first one's just a comment about the paper itself. So just wasn't sure who the audience of the paper was. Right? So it wasn't clear to me just in the way the paper was written whether these interesting observations about, for the classical methods, or for the frequentist methods, you get this formula, but for the Bayesian, it's a less than or equal to. It wasn't clear to me whether this was sort of not well appreciated in the statistics fraternity, or whether it already was, but you wanted to present it in a user-friendly way, or what exactly was the contribution of this bit. I mean, it made a big contribution to me, but that's because I wasn't really aware of this stuff already. Right? So that was sort of more from the point of view of the statistics audience. From the point of view of the philosophers audience, I think it might help to connect the Bayesian analysis up with some more standard Bayesian treatment, or philosophers' standard Bayesian treatment. So I think philosophers in general are not used to thinking in terms of what's the expected performance of an estimator, right? I mean, it may distribution over them. Once we get our evidence, we're going to update our prior distribution to get the posterior distribution given the evidence over this parameter value, right? And then maybe we want to do something at the end, like find the best expected value of the true value given our posterior distribution, right? Where that should have the minimum squared error, right? If you just take each value, multiply by its posterior probability, and get the weighted value of the true value. So the point is just, it would be nice to see how this sort of Bayesian assessment of the estimator connects up with just finding the posterior distribution and then singling out a value for theta using your posterior distribution, right? Which I think is the kind of the way that many philosophers would be thinking about this type of problem. Okay, and if I have time for one.
Yeah, that's a quick remark,
Yeah, so the final point is just, because I'm interested in this distinction between the Bayesian and the frequentist. I mean, it was interesting to me because I've come around to thinking that this focus on priors is a bit of a distraction, right? So, often the difference is cashed out, like, the frequentist just thinks about the probability of the evidence given hypotheses and doesn't sort of make up probabilities for the hypotheses or the true values themselves that seem to just come out of nowhere, right? That are just subjective probabilities. But anyway, my own view was that that's a bit of a distraction, and the real distinction is that the frequentist bases their inference methods. They want to do inference in a way that has the best expected results given all of the ways the evidence could turn out. Right? So they're assessing the quality of their inference procedure. Right? Whereas the Bayesian doesn't really care about all the ways the evidence could turn out and the best, the expectation of accuracy or whatever, given all the way the evidence could turn out. They're just interested in the evidence that actually happened in this case and making the best inference given the evidence at hand. Let's forget about what other evidence might have appeared. And so that's linked with the likelihood principle and, the Bayesians respecting the likelihood principle, I'm sure, and the classical statisticians not. So anyway, I was getting a little bit confused because in this paper, the emphasis was back on the priors, and we had both the class frequentist and the Bayesian seem to be assessing the long-run performance of an inference method, rather than distinguishing the Bayesian in terms of, no, once we've got our evidence, then we just narrow down and consider how good the estimator is with respect to that evidence at hand. So that was just an observation.
Yep.
Thanks.
All right, so this was, thanks for this. This was a lot, but I'll respond to what I can. So first, so let's talk philosophy. Okay, so I think you were absolutely right that the philosophy of probability has tended to overemphasize the objective interpretation of probability as the hallmark of frequentism, where in fact, one of the things that I see as the hallmark of frequentism, perhaps, often philosophers will read Eckhart von Mises or somebody like that, when perhaps they should be reading Abraham Wald, which is much more influential and I think a much better representative of that school. And his main concern is rather with things like worst case scenarios, and he has all of these minimax methods and minimax theorems and so forth. And so it's a concern for robustness and for the logically worst thing you can imagine. Whereas as a Bayesian, you will say, well, that's a marginal issue. You know, we can afford to disregard or effectively disregard some things. So I think there's a real issue there, and I would welcome a change in emphasis as well, or maybe a rediscovery of Abraham Wald in philosophy. Then there's another thing about the long-term performance or the long-term properties of different estimators. And here there's a crucial distinction which is quite important to make, which is that well, you can be long-term in 2 dimensions, right? You can get lots of data, or you can repeat the same experiment with a small data set a lot of times. And all of these estimators are equally good in terms of big data sets. So they're all statistically consistent in the sense that they always converge to the correct value. But all of this only is about small sample sizes. It's an issue that only has to do with what do we do when we have 3 or 10 or 30 data points. And this is where bias, because that's where you may end up being confused by noise. If you have a gazillion data points, then the law of large numbers is going to wash out anything, whatever kind of statistician you are, almost. So that's not the issue. The issue is when you've seen 0 data points, what kind of statistician are you? What kind of assertions are you going to make? And if you really are a Bayesian, then you have an opinion on things after 0 data points. And this is what Ronald Fisher will be screaming about at that point, or Keynes for that matter. Then there was well, then there's the audience issue. Well, this comes out of, I mean, I suppose that it's sort of in the subconscious of everybody in machine learning that this is a frequentist theory. But the thing is that none of these people are frequentists who are teaching it, right? So it's being reiterated and given as, not explicitly as a justification, but being taught as like a fundamental fact about how we deal with things in statistics. But nobody seems to notice the philosophical dissonance between those things. This was really what motivated me to write what I figured this was a philosophical paper, right, called Meditation in the title. Yeah, because there's no, I mean, nobody's having a statistical problem, and nobody would gain anything on the statistical level by reading this paper. But there's something odd going on at a conceptual level, I think, and that was the point to point that out. Okay, last issue is you're saying estimators, and this is sort of a strange way of thinking about it, and like using variance instead of, say, entropy and things like that. But I think it's important to remember that if we have, let's say you're a Bayesian, or you're perhaps a Bayesian in a frequentist router. You think there's an actual underlying real probability distribution here. Then you get a data set X of some size, and now you want to, based on that data set, come up with a posterior probability distribution of some sort. This is also, in a sense, an estimation problem. You want to have these 2 things look a lot like each other as fast as possible. So, for instance, if you had like the 2 bins here, this is heads and this is tails, and then there's a question of, I can put in some like some pseudo counts and give them a few extra counts before we even start the experiment, and then I can start counting actual observations. Then there's an uncertain issue of how many extra counts do I put in here. So that will change. It will correspond to a different prior than what I'm doing here, but seen from a sort of different angle, what I'm doing is choosing a different way of converting a data set into
into an output distribution. So in a sense, I'm still solving a guessing problem. Right? There's something hidden from me, and I want to come up with a way of looking a lot like the hidden thing very quickly based on the data. The only thing is that there's using variance-based or like squared error-based error measures is not as natural here as it is in the case of estimating a number. So usually you would use something like some logarithmic integral instead. You're looking at differences between two probability distributions. And then this is going to look a little bit different, and we're not going to get the same theorem. But in principle, you could also use, there are some Euclidean distant-based scoring functions which have nice properties too. So this was just like a long speech to say that just classical inference, Bayesian inference, is in fact, when you like look at it in the right way, also a kind of an issue where you have to choose for no particular reason to translate data sets into distributions, and that's also an estimation problem.
We can talk about that.
All right.
We have maybe time for one or two quick questions if there are any questions. Yeah.
So, a lot of this stuff is very foreign to me. But so when you play a Bayesian game and you start with a beta distribution, you start with beta 1, and then you have one of the uniform,
Yeah.
right? And then you have one observation. When you beta 1, 2, will give just shift right away. Right?
Yeah.
And then your expectation is going to go to 2/3, just like an h plus 1 over n plus 2, right? So why would anybody think it's h over n? In the Bayesian game, it's just straightforward, isn't it?
I don't think anybody in the right mind would have a Bayesian estimator that would just be the empirical frequency. I mean, that would be incredibly stupid. You would assign 0 probability to way too many things to do. I don't think in practice anybody does that. I mean, there's so much blood and sweat and tears being spilled over smoothing methods. I mean, going back to Bletchley Park in the 1940s. So I don't think anybody would do that. But it's different if you're Ronald Fisher. Then there's only one maximum likelihood estimator. That's that one. So you get two different arguments that are both saying there's only one rational thing to do, but different odds.
Anyone else? So having survived a day of mathematical philosophy, you definitely deserve a reception, which should be ready in the registration room. Let's thank the speaker.